Hello and welcome to another episode of Mental Mom Interviews. For this episode, I'll be talking to Dr. Jabir Husiny. I hope I pronounced that correctly.
Yeah,
And I'll let you introduce yourself.
yeah, for sure. So first off, I don't have my doctorate. I just did my master's. But my name is Jabir Husseini. I'm a recent graduate. I finished my master's degree in Dr. Eric Lyon's lab, looking at winter wheat, more specifically looking at winter wheat physiology and morphology pertaining to low temperature flooding and ice encasement events in Ontario. And I'm currently working full time as a research technician at the University of Guelph. And I'm still working on the wheat projects. So, yeah, little brief interview.
So are you working on your PhD as well, or are you waiting on that a little bit?
Uh, Not at the moment. Maybe down the road, but yeah, working right now.
Fair enough, fair enough. So can you give an overview of the project you did for your master's?
Yeah, so for my master's, I basically had to develop, um, you know, I used existing methods and implemented newer systems to develop methods for screening or testing uh, low temperature flooding and ice encasement tolerance of winter wheat cultivars in controlled systems, so indoor environments. So using growth chambers, I grew them to a certain growth point, which was in line with the literature, and then uh, acclimated, then induced the treatments, which were low temperature and ice encasement. And
So I have a quick question. So what are the methods used for this process for
yeah,
screening?
yeah, good question. So um, the methods used were using controlled systems, which, as I mentioned earlier, starting out with just figuring out what growth media we're using. Um, if you look through the literature, that's like one of the basic things you look for is just like, okay, how did they grow the plants? What nutrients did they provide? Um, and then to what growth stage? And then at that point, how did they acclimate? So figuring out like the environments. Um, so going from one chamber to another, given the limitations in space, and then how do you induce the treatment? So like what temperature points do you pick for the plants without killing them immediately? So you have adequate data from when they survive to when they start to die off. And then also how do you apply ice? Kind of like how you would apply ice in a freezer when you make little ice cubes, do the same concept to the plants and see how does that impact their survival and trying to isolate those variables. So there isn't like one specific method used. There was a bunch of methods incorporated.
So you more or less put these plants through a simulated version of what happens in nature in different sections to get a more holistic view of how each of the plants operate under these circumstances.
Yeah, I would say that's a good description. Yes.
Excellent. Continue with your overview.
Yeah, so with these methods and doing these different tests, we used, or I guess I used, 4 cultivars just because of space and time limitations. And so I had to pick cultivars or wheat varieties that were, um, I picked 2 that had known properties, so 2 positive controls, which were a really hardy cultivar that's well studied, North Star, which I think I'm sure Rachel or Alex would have mentioned this in their
Yes, it
podcast.
is.
And then I also used AC Carberry, which is a spring type, as my other positive control because I know how they would behave and it would give me an indicator of how the methods were and were not working. And then I also used, as my 2 test cultivars, I used 2 Canadian Eastern soft winter wheat cultivars that are grown commercially, so Branson and CM614, to see how would they fare under these conditions, because a lot of the literature, when you look at winter wheat in Canada, it's mainly done out west in the prairies. So, and their climates are a lot different than ours, and so using those methods, we wouldn't necessarily get the same results. So I tried to make this more focused to our our conditions and the environments that we see. So, which was a challenge in itself. Given how drastic the weather changes in such a short period of time, and our winters are getting more mild and a little bit more unpredictable. Like as you saw this past winter, we had a lot of freeze thaw cycles, which caused ice encasement. So it'll be interesting to see the reported losses and data for that as well.
So, what traits make different wheat varieties are able to survive ice encasement?
Yeah, that's an excellent question. So that's so from a physiological perspective, starting out with things like how tall the plant gets, how quickly it produces tillers. Um, Typically in the natural environment, especially in Ontario and more specifically like in growth region 2 where we're at, a lot of farmers will plant probably the second week of September, so that by the time winter arrives, the plant's developed enough that it has adequate time to acclimate and then overwinter. So other traits that are important would be sugar levels. In the literature, you'll see there's been certain sugars that are associated with survival. So looking at fructan, sucrose, and simple sugars, which is another aspect of my research that I had to do, was going to the lab and assess sugar levels during non-acclimated, acclimated, and ice encasement, to see how do those sugar levels change and does that correlate with survival. So those are two that I would say off the top of my head. It's just like development and sugar levels.
So now that you finished the master's report, what results did you get from it, and what conclusions do you draw from it?
Yeah, good question. So it was a process trying to figure out all these different environments and getting everything to work. I think I must have done like at least 10 to 12 test runs before I got something to work. But so I basically did three major projects into my master's. So I did what's known as an LD50 test, which stands for the lethal dose, or lethal, in my case, lethal days to reach 50% mortality. So I did like curves to estimate the 50% mortality rate. So for that, I would hold the plants after they've been acclimated at a consistent temperature of -4 over time and see at what time point does it start to veer off, to see like how long they can withstand a consistently low temperature. And then I also did and within that I also had other variables such as ice and no ice, to see how does ice on top of the cold affect survival. And then I also did an LT50, which stands for lethal temperature. So in this instance, I followed the same protocol, and after acclimation, I would decrease the temperature over time and hold. So I had a deep chest freezer that was capable of going down to very low temperatures, and I would start it at -4, and then it would ramp down to about -19. And it would do it incrementally over time. So it would take like an hour to ramp down, an hour, it would hold it at that temperature, and then move on to the next temperature. And at each temperature point, I would sample plants out and thaw, and then move to a greenhouse to assess for survival. And then the third one was the biochemistry. So looking at fructans, sucrose, and simple sugars at those different treatment points. So, and what I found, so in the LD50, as you would expect, the longer you hold them at a consistently low temperature, the survival decreases. And North Star of the cultivars had the highest LD50 because it's the hardiest. And then I didn't really notice a difference between the ice and no ice treatments, but that's something that we could further test to make sure there isn't. But in my study, I didn't. And the same thing in the LT50, I didn't see a difference between ice and no ice treatments, but I did see cultivar differences. And as you ramp down in temperature, there is a threshold, and beyond that threshold, the plants die off pretty quickly. And then in the biochemistry, there was spikes, which was good to see. So from going from non-acclimated to acclimated, you saw a spike in the carbohydrates or sugars, and then during ice encasement, it would further go down, indicating that they're being used up because they're basically energy storages. So those are some of the general trends that I saw in the results.
So if I could just draw a conclusion from here, would the amount of fructose and sugars increase the cold hardness and therefore breeding for more and more fructans and sucrose, further increase the survivability of such cultivars?
I wish it were that easy. um, the answer is never that easy. It the, it is associated with hardier cultivars, but the issue is when we scale up, growers, yes, surviving is important, but if those are the only traits you're looking for, they're more interested in yield, right? So that you have to make sure there's a lot of compounding variables that you have to incorporate. So that's a tough one to answer, and I don't know if I have one answer for that.
No problem. So of the cultivars, which one do you think survived the best
Yeah,
outside North
so
Star?
yeah, so given the size of my experiment, I don't think the cultivars were more of like a way of testing the actual method. So this was more like a method development thesis. So the cultivars weren't like the main focus, but amongst the cultivars, North Star was the hardiest overall. But the Ontario commercial varieties, Branson and CM614, weren't that far behind. So they're still pretty hardy, I would say. Uh, if North Star was the hardiest, they're a close second.
Excellent. So if you could change anything from your experiment, would you make any tweaks or anything like that?
Yeah, that's. I wish I had more time and space. I would expand it to have more cultivars, more samples, and also more environments so that I can see, uh, a better picture of everything, and also just having more continuous data points. So just going from for the LD and LT50s, just having more data points that I could pull from because of the limitations I had. I was limited to like 6 to 8 data points on each side. So what I mean by that, like for instance, for the LD50, I did 0 to 32 days sampling. So I did like 0, 4, 8, 12, 16, 20, 25, 32 days. And then for the LT50, I did -4, -7, -10, so on and so forth, down to -19. Uh, so yeah, just being able to scale up, and then also if I had more time, I would also do like a field component to see, how does this work in nature?
Yes. So if you could refine these a little bit more, these processes a little bit more, what would you add into the mix outside of space and time?
Yes. I would assess probably protein levels, because that's an important thing, especially for growers. So like beyond their survival, how does the plant, what kind of proteins does the plant have and nutritional value, given that it's a grain, that's what people care about. And also, um, uh, probably like respiration rate, like oxygen levels. See, like, are they, what, especially during ice, because a lot of the literature says the causal issue of ice encasement, or the causal damage of ice encasement, is like anoxia. So elevated levels of CO2, ethanol, and seeing like those respiration rates and being able to quantify that would have been very cool if I had the means.
So would you, if you ever got the opportunity to do a PhD thesis, would you test that into it?
Yeah, I mean that could potentially, yeah. I mean, that would be cool. I think it'd be very interesting to see. Um, I think it'd be a lot of work, but might be you might be onto something.
Thank you. So if, as it stands right now, your the results of your thing and results of your project, sorry, and how these methods have been set up, are they a perfectly suitable form for testing for frost tolerance, or does it need to be tweaked a little bit more to be more refined for the mainline sort of methodologies within screening methods?
Yeah, I mean, I think it's a good working method, but like anything, it can always be tweaked and improved. And I think that's where testing over time would help, uh, and testing with different, you know, plants, different tools, uh, different environments. But overall, I think the working methods I published were fairly good. Um, I think the one issue I had was ensuring that the non ice encasement plants, the soil was like fully desaturated. So I think one of the issues I saw was amongst the ice and no ice treatments, there was no differences. And I suspect because the soil of the no ice treatment was still saturated, so technically it may have still encased the soil in ice, if that makes sense.
Yes, that makes sense. Uh, so based on the results, can you give any advice to common plant breeders to say what you should breed for given these results? If so, what traits would you tell them to breed for to allow for better survivability over winter?
Yeah, it's a great question. It, the thing I would say is probably some of the basic things like ensuring plant height, stem thickness. Um, so not breeding for too tall of a plant or too short of a plant, somewhere in the happy medium. Uh, ensuring like stem thickness, because usually when you have a really thin stem or a really thick stem, it causes other issues. Or, in terms of carbohydrate, usually plants that have, if you're just breeding for winter tolerance, plants that have higher levels of fructan, simple sugars, and sucrose tend to survive better. So I think those are the three I can think of off the top of my head, but that's a tough question to answer.
So what would be the happy medium for plant height and stem thickness? What would be the best suited forms?
Yeah, so like if we look at North Star, for instance, it grows a lot more horizontally as opposed to growing very high vertically. So it almost looks like a bush when it's at like before it starts before the stem starts elongating. So, I mean, if I want to quantify it, I would say like the average height of the hardier plants that I notice in the field when they're ripe is probably around like 2 to 3 feet. If that's it, does that answer your question?
Yes, and for stem thickness, how wide would the stems be? How thick should the stems be in order for it to be the happy medium?
Yes. The stem thickness. Let me just double check what I got here. But off top of my head, I don't know if I have the answer for that right now.
No worries.
Let me just look that up for you though.
Thank you.
So I'm just pulling up the results for my thesis.
No problem.
So during uh, non-acclimated to acclimated, the stem thickness was about. So this is like during the early seedling stages. The hardier plants like North Star had a stem thickness of about 0.5 centimeters.
Ah, excellent.
Yeah.
So these two points would make it very hardy, correct?
Uh,
Or increase the hardiness a little bit, right?
yeah, I think that's a better. I think there's a lot more variables you need to consider. And these are I'm just pulling these from my own thesis. There's a lot of other literature that points to other factors. So these are just two that I listed.
So, given the current trends and our current mild weather, what would you recommend plant breeders breed for going forward?
Oh, that's I mean, far, so it depends what the goal of the breeding program is. So most breeders will plant will breed for things that will have, you know, higher yield because they're concerned about feeding the general public or, the helping the growers and producers have more outputs. So if that's your goal, then yeah, breed for plants that will have higher yield, which directly does correlate with, or there's a relationship between plants that survive better. If you think about it intuitively, if they have better survival, they should, in theory, produce more because even though one plant might be, has like 50% survival as opposed to 70% survival, the one with the higher survival should yield more.
Makes sense. Thank you. So I'll end this thing off by asking you if you have any last statements you want to give to the audience.
Uh, yeah, I mean, it's a complicated problem. That's why I'm sorry if the answers weren't as clear cut, but given the large scope of the issue that we're trying to deal with, which is, the changing weather and different uh, factors like ice encasement, low temperature, and flooding, which are such large issues, it's hard to try to isolate and figure out those problems and how to overcome them using simple experiments. So I think more testing over time with larger scales and different systems should hopefully give us a clear picture of how to go about this moving forward.
Thank you.
Thank you.
Well, that about covers this episode. Thank you all for watching.
Thank you for watching this video. If you enjoyed this video, please like and subscribe. If you really enjoyed it and think you can donate, you can do so at Buy Me a Coffee, link in the description below. Thank you for watching.